Welcome back, guys, and this I think is going to be a very interesting video for everybody. I did a lot of different things here in the shop getting ready here for the speeds and feeds. And first I just want to show some experimentation I did with drill bits and taps and hole sizes, so hope you enjoy it. Okay, I'm hoping to save you guys a lot of time and work and effort on drilling and tapping and a bunch of things, because I know a lot of you guys don't have gauge pins and maybe setups to do this, but I was watching a video, an Australian guy showing how to calculate the correct drill size for a specific tap, and of course, being Australian, he was doing it for metric. And he was saying it's the tap minus the pitch equals, yeah, the drill size. Alright, so for instance, he was like a 4mm tap, and the pitch was 0.7, and it came out to be 3.3 millimeters drill bit that you need. Fine and dandy. So I'm wondering about what the great old machinist handbook has to say about it. And they've got a whole different world. They're saying, and I'm sure they got to be mathematically on it because they come up with some of these crazy numbers. So for metric, they're saying the basic major diameter, just major diameter, minus, look at this, 1.08253 times the pitch, times the percent of full threads. So if you want 100% of full thread on it, and I did the math on this and it comes out real close to this. It was just slightly, I think it was like 3.31 millimeters. And the American too, they had differences. You know, the American, another video showing, I forgot where I wrote it down here. Oh yeah, no. Yeah, 1/4 20. Yeah, so if you had a 1/4 20 tap, you're going to say 1/4 minus, put the 1 over the 20, and it equals, that's it, right? Yeah, I think that was it. And then the machinist handbook, you can look it up. It's another crazy one which comes in nuts. So yeah, these are matching here, and they're matching the charts that are everywheres on it. Let me make sure I'm right on this 1/4 20. Right, alright, clear. 120. Alright, clear this out, right? Memory, clear memory. Clear everything. Memory recall 0. Alright, 120. 1 divided by 2, 0 equals that. Oh yeah, 0.05. So 0.25 minus 0.05 equals a 200 drill bit. Where's the 1/4 20 number set? Yeah, that's correct. So that's it. 0.200, which is like the number 7 in drill bit in the chart. So that's an easy one. So now, all fine and dandy, here's the formulas. I can use the really complicated ones for both metric and imperial, or I can use a chart or whatever. But then I'm looking at, alright, fine, I know not a single drill bit is actually the size of what it says. So you can do this and you can say, okay, that's the size, but now what drill bit, because none of them are going to be exactly what you need, so you got to come close to it. So I measured, what I did was I took the brand new Cobalt set, because it's really nice. I took the 1/4 inch set, a 1/4 inch bit, and I did it first with a thick piece. You know, you can see there's differences here. This hole, if I drill it out 250, I drilled it all the way through, and then I used gauge pins to check the hole size. It came out to be 0.258, 8 thousandths bigger than it should have been. If I mic the drill bit, because they're not 250, it was actually 0.247. So we're talking, it oversized the hole 11 thousandths. I did it on this, and then I did it on this one. Now, in previous videos, well, it's because all the chips that are coming out are kind of creating a mess at the top here. And you visually see it. This is all like screwed up. But the chips evidently are eating away in here too and making it oversized. So in other videos you always see me undersize the hole first. So this was the actual one that I did undersize. And instead of the quarter, it was the next one down. Drilled it out, and yeah, total mess. And then I put the 1/4 inch bit and went through. And to my surprise, the drill bit was 247 and the hole was 247. So undersizing it and then doing the final size is almost like using a reamer, because you clean the entire hole up. It looks beautiful from top to bottom, and it turns out it's the exact size of the drill bit. So that's just kind of getting some things under my belt, and I hope this helps somebody out. But I'll probably use the machinist handbook. I'll put this formula, type it up on a little nice chart, and stick it on the side of a toolbox, and I'll be using that because, you know me, I'm Mr. Precision, so I'll be using that to come up with what the hole should be. And then caliper or mic, I've got the metric set, the fractional set, the A to Z set, so see who I can come closest to. Plus I like the ability to say, well, how much percentage that you want in threads, because the percentage is, and you do it in a decimal. So in other words, if you want 50%, it would be 0.5. So you'd have this number times the pitch. If it was a 1/4 20, this would be 20 times 0.5 would give you 50% threads. And then that would tell you the drill bit size. So I like the ability to do that. And so I can say just exactly how tight it's going to be. So I hope that helps somebody. Alright, main feature, feeds and speeds, or speeds and feeds. To do this, I know I'm going to be checking or testing different materials, 1018, 1144, aluminum, so on, for finishes to see. And I'm going to be, because of the different materials, using different cutters. So I want to remove any possibility that a cutter is a variable. So I have to scientifically, so to speak, check all the cutters and that they're on height. So let me take you to the lathe. I did this on both lathes. Take you to the lathe and I'll show you how I figured out where rotational center is and how I checked all tools, all cutters. So to figure out where exactly center is, rotational center, to 1,000th is pretty easy to do. First, piece of 1/2 inch aluminum goes in the collet and you turn it. Now if I mic it, that I know without a doubt I have a known distance from rotational center to the surface of what I just turned, right to 1,000. Now all I do is I put the new Noga indicator holder here with the dial indicator and zero it out on the very corner of the compound here. So I'm zeroed there. Now I can easily take the cross slide in, lifting it up, and set it on top and find the peak. Now I know the distance from the top to here to 1/1000th of an inch. Divide that in the diameter here in half and subtract it from the measurement. Now I know exactly where rotational center is from this surface. And it's a kick because it turned out to be 666 thousandths. So now let me take you over to the granite surface and show you how I'm measuring where my tools are. Alright, I know I'm going to be in the way for some of this, but you can see I put the finest little point on the dial indicator. You know, the Noga goes on the base that I described. This thing is fantastic. So now I can easily zero this guy out with that fine-tune knob. See, there it goes. So easy to do. Just beautiful. Yep, a little bit over. That's why I need to get my hand in there. My disc might not be perfect. Down a fraction more. There. So I'm solid here. I can tap on it. Doesn't move. I'm slightly under the zero, but it's a good reference point. So I take the tool holder, and I'll just take, not that guy. Take this guy. Stick him in there. Clamp it down. Alright, so I'm in there. And now I can take this guy and I can set it with the magnifying glass right on the tip. Right on the cutting surface. So walk him in. Yep. And it's pretty easy to get it right on the tip too. There. So I'm at 661 thousandths. So I am 5 thousandths below rotational center. So I've been doing this to all my tools and I'm finding out every one of them is off. And I did take my favorite cutter for aluminum, the one with the TCMT, measured it and it was pretty far off. I forgot what the number was, but I played with the thumb screw, put it right on 66 thousandths, 666, did a facing on a piece of aluminum, and it was perfect. So I'm slowly setting up for my old lathe all of the tools so that they're right on rotational center. Let's see if it makes a difference. I did do the same thing with Dan's insert, that one that I've been experimenting with. It was way off. I think it was like 15 thousandths too low. I put it right on rotational center and unfortunately didn't really get a significant difference. The finishes that I'm getting is still the same thing. So that's how I'm measuring them. And as far as too high, too low, does it make a difference? I don't know, but I'm gonna find out here over time. Alright, like I said, I wanted to make sure all the variables are kind of removed or at least explored. So next up I'm going to show you a quick little test I did on the compound to make sure the gib is good and stable. Alright, I got to hand walk this thing. I wanted to see if the compound is moving, thus the tool is moving when I'm doing cutting. So I've got 1144, ½ inch in there. I've got Dan's insert in there. And you can see the Noga is on the compound. And I'm just sitting on a disc. And I think I can get the camera to sit someplace here where you might be able to see the dial. Yeah, I don't know how well you can see the dial. It looks blurred out. What happens if I move this? There you go. Alright. So you're looking at the dial, and the spooky thing is if I grab the compound and I try to tweak it, it's not moving at all. That's unreal. And the same way when I walk back and forth here on this disc, it's not moving. But if I give it some power here, and I give it a 3/1000ths cut, as I go in, the needle does not move. So I don't have any problems with a compound issue here. We're actually getting a pretty good finish. Yeah, I'm getting a real nice finish. Now, there's grooves all over the place, but way better than I had before. But it was really interesting to do this test to see if, and yeah, I can tap on the Noga and you can see the needle bounce here. So, wow, pretty good work on the compound. Okay, so all my experimentation is going to be in my old lathe here, because it's already got the CNC, but I've got the new laser tachometer. So first part of this video, I'm setting up speeds. So I need to know the RPMs, and I explain how I did it. And then the next thing I'm doing is, just for the grins and giggles, figuring out with the gears in here and the power feed as it is, how much does it advance per revolution. So here's a learning curve. Alright, just playing around here with the speeds and feeds and experimenting. This is a 1018 that's in here, and I'm using Dan's insert, so I know I don't need to invest in any other inserts or even contemplate playing with anything else, because I know without a doubt this insert can do a killer job. So it's just a matter of figuring out what's wrong, what am I not doing right, or something here that I can't get a gorgeous finish. So the first thing I did is, I've got the tack here, and I was thinking about just making marks and writing in the RPMs, but then I thought, okay, all the guys with the big Atlas lathes or whatever, they only have a certain amount of speeds. You know, they move a lever and they go here, here. Some of them, yeah, have variable pulleys and so on. So I go on Google, look at images, pick one lathe at random that I can zoom in on, and I can see the control panel on it and the speeds. And I was surprised actually to see most of it is low RPMs. This one lathe I was looking at, you have a choice of, what is it, 6 settings: 130, 300, 400, 600, 1000, and 2000. So I'm figuring, alright, these guys on a big lathe can do killer finishes with these speeds. So forget maybe thinking about forgetting the charts where, oh no, you got to turn it at 650. Well, this guy can't because it's fixed at 600. So I just made some marks here. First one is 300, 600, then 1000, and then way up here this tick is 2000. So I tried doing a finish. Let me zoom it the other way, tilt this over and kind of telephoto in a bit. Oh, it ain't gonna work. Alright, let me reposition. Alright, so I'll zoom in more so you can really see the needle here and what I'm trying to say. But there's the finish, 1018. I ran it auto feed, I ran it manually, and I ran it at some of these RPMs and looked at a chart and said, okay, you're supposed to, I think it said 1000 RPM, but the key point that I want to make, let me open this up, and there's a piece of tape here, there it is. So I'll have to tilt this the other way to be able to, the camera to see it, there. Point is, I'm going to put this in power feed, so I move it up. So now if I engage the power feed here, it'll move that way from my right to left. So zero this guy out. Oh, I'm moving the wrong thing. Oh, I gotta move this to do it. Alright, well, I'll put the needle on close to 0. There. No, not gonna stay, is it? Yeah. Tap on it. Alright. So the tape is up and I'm on 0. Now if I move one, oh, I gotta engage it. Oh shoot, okay, well that's going to throw the needle off all over the place. And there's no way I can do this Let me try redoing this whole thing so I'm on the compound. Alright, so now I've got the magnet on the compound, so I can adjust this thing. Right? Is it moving? It's not moving. Oh, it moves in. Well, why doesn't it move out? Yeah, there it is. Okay. So, let's get it on 0 nicely. Alright, we're on 0. So now, the power feed's engaged. It's going to move from my right to my left. And I've already spun this, so I've taken up any play or backlash that's in there. The point is, tape's up. If I go 1 revolution, and I realized putting it on the end of a rough piece of 1018 wasn't a bright idea, so there, the tape's back up. So that moved, what is that, 4 thousandths, 4.5 thousandths. Yeah, that's what I measured before. So, okay, for every revolution, I'm going to advance 4.5 thousandths. Now, if I'm spinning at 100 RPM, I'm still going to get 4.5 thousandths per revolution. It's going to travel from my right to left very slowly because I'm at a low RPM. If I go 1,000 RPM, I'm still going to get 4.5 thousandths feed per revolution. The only difference is I'm moving from right to left faster because I'm spinning at a higher RPM. So the point is, with this lathe, all you're going to get, unless you change the gears, is 4.5 thousandths per revolution. It doesn't matter what speed, what RPM you're running your chuck at. So, yeah, if it's 4.5, let me zoom in even further here on this needle. Ah, there, you can really see it now. So if I go another revolution, that should be 9 thousandths, right? Okay. So let's just take it around one more time until the tape is as visually up as I can get. There it is. And I'm at less than 9. Interesting. Actually, look in the camera. I can read it easier. Yeah. So that's curious because that tape is, yeah, up. If I moved it a little bit more, not, yeah, that's 8 thousandths. Wow. So something is different with this feed. Let me move it one more time. Let me see if I can get it on the 10. Which way do I gotta go? Oh, wrong way, Dave. This way. There. That's pretty close on the 10. So if I move it one more revolution, do I get 4.5 again? There. And no, I don't. I'm getting a lot less. Interesting. What is that now? That's 10, 11, 12, a little over 13. 3.5. Try zeroing it out again. And see if I get the same thing every time. Rotate it. So there's definitely then, this is telling me that there's pitch or something issues. That's 1, 2, 3, 4, yeah, 4 thousandths now. So there is definitely pitch issues in this lead screw here for the power feed because it's getting different numbers. But the point is, this is on the lowest feed rate possible with the gear ratio that's on there. And it doesn't matter what RPM you're using because you're still going to feed at the same rate and cut material at the same rate. So they're linked together, rotation and feed. Try this setup one more time because I think it was operator error. This was flexing down. So now I've removed the quick change tool post. I'm rock solid on top of the, tapping on it. You don't even see the needle move. Rock solid on the compound and put it back. Also, because the camera's leaning, I'm looking at the needle straight on. and the camera can't see it because it's at an angle. So when I said it's on the 10, it looks like it's 10.5 or a little bit over it. So, and I'm going to turn it with the wrench to keep my hand off the chuck and possibly messing anything up. So now I'm looking at the camera thing going, alright, I'm on, as far as I can tell, very close to the 20. It's not exact, I don't think, but 1 revolution. There's 1 revolution, and it moved, looks like almost 4.5. So if I do it again, I should be at 9. So 1 revolution again, there, and I'm almost at 9. So there is still some pitch issue. Let me see, back it back up to the 20. Looking at the camera, there. Alright, it could be because I'm not perfectly up with the tape. I should have something else to do this with, but it was almost 4.5 again. So yeah, it is starting to become consistent. I did have operator error in there. Try it 1 more revolution. Do I get the same reading? And there you go. Yeah, it's almost at 9. Actually, it's at 8 now. So that's a little bit worse. And that tape is pretty much so up. So, alright. Enough of beating that to death. Yep, there's the problem right there. Run out on the ER32 collet chuck. So I would have to do this back on the base, and hopefully there's no run out there. But still, my point's made. Doesn't matter what RPM you're at, you're cutting the material at the same surface feet per minute.